So here we are. I'm just checking in parallel the video from the morning, and now it should be, no, it's not uploaded fully yet. It's 63% uploaded to YouTube. And from the OneDrive, the link where you can pick the files for offline viewing, I'm just checking the status there. One moment, please. And there I see that it should be already there. So the morning session should be on the OneDrive link in the lecture area of Relax. Okay, so here we are back again. Before I continue with my monologue, I'm listening to your questions and drinking some cold coffee. No? Not yet? Huh. Okay. You haven't just catched the requirements why we should um, um, understand or why we have this disturbance at all. Okay. So the disturbance itself. One moment. Here we learned that if somewhere the concentration is increased somehow, we will learn later how. Then we have a flow rate. That means a concentration difference and concentration gradient results in movement. So movement is current, and current is device. So within a device, we generate current not only by pulling them, but by changing the concentration. Now, we learned here that if you manage to change the concentration, then you switch off this change, then the concentration goes down again step by step as a function of the time. And this is this curve. But we haven't learned how and where this will happen. These are just the alphabet of our words to build the sentences. So, first, concentration difference, movement. Second, you pull it, movement. Third, the concentration difference is somehow generated, then you have a certain disturbance, certain injection level, which is higher than before. And we learned how to calculate this level at all in a certain semiconductor. So we have all the tools to calculate the current in the device. We should understand how it works. That's the reason behind. Does it help? Okay. Little bit or completely? If a little bit, then put a second question on top. Okay, okay. So in the lecture notes, you see just the relaxation time. I would like to give you some additional information on this figure. If we go to the spreadsheet again, and if we go to the second area silicon data, there I have also put together this lifetime as a function of the doping level. So take the left axis, the lifetime of the electrons, as a function of the doping level. So the lifetime itself, see here, the black curve. If we have 10 to the power of 17 doping, we have a lifetime of quite long time, 10 to the power of -5. And if we have towards ohmic contact, so we are 10 to the power of 19 towards 20, the lifetime shortens. Okay, so the acceptor doping shortens the lifetime because of the presence of the hole concentration. And the lifetime uh, of the holes in n-doped, donator-doped semiconductor, we have also this behavior. So I have a spreadsheet where this figure is just fixed to, for the holes, 35 microsecond, and for the electrons to 80 microsecond. But in reality, this lifetime is a function of the doping level, which is the orange figure. So in my case, the doping is defined by U, the orange area, and but in reality, this is not a blue figure. It is not a constant. Be aware of that. I should have made a fitting curve to this measurement, and then you can put here the fitting curve equation as a function of the doping level. But I haven't done that for simplicity because I was too lazy for that. So be aware for making these assumptions in this spreadsheet. Okay, let's go back to the slides. Okay, now we go on to the core equation of semiconductors. We will not derive it in mathematically way of thinking. We derive it by understanding the behavior of the particles. So the continuity equation, for this equation, we start with a cube. What does this cube mean? So this is the surface, this is top, this is the right-hand side, and the dashed area, that's the back side, and this dashed area is the bottom side. Okay, here we are. For the continuity equations, we check in one direction, only one direction, the current density. So let's check the current density in the x direction. Okay, what happens to the current density if we measure the current going in this surface, and then we measure the current going out of this surface on an dx area further away. Okay, so let's assume you look onto a surface and there the current is flowing into this surface area, and a small portion behind the surface, the current is going out of the surface. Now you look on at these current values, current densities. Now let's make an analogon to in physical area where we can grab this stuff. Assume you have a bottle, a large bottle, and you plug in a tube where the water flows into this barrel, let's say. Okay, so in the x-axis, we have a current flow into this barrel. And a certain x dimension further away, we have an additional plug, and there you have the water is pouring out. In this example, assume the water current into the barrel and water amount out of the barrel per second is equal. The flow rate is equal. Then look into the barrel. What happens with the level if these two are equal? For sure, the level keeps constant because the in and out are equal. Okay. Now, is it better for you to have for these hand descriptions this video here or this video here? Which is better for you in your environment? Doesn't mind? Doesn't mind. Both are crap. Okay, no. Then I will keep only this video because I see me twice and this makes me very sad. It's enough to see me once. Okay, so now let's change this way of thinking. The current density at x is higher than the current density at x plus dx. Then the charge density is increasing. The water level is increasing. And exactly this is the equation for charge maintenance. What does this charge maintenance mean? We have linked the local change with the temporal change. Again, we have linked the dx instead of three-dimensional, we can think one-dimensional. It's okay. So the local change of the current density from here to there, we have linked to the change of the charge density as a function of the time. So time is linked with the location. This linkage we will use, okay? So if we do this one-dimensional, if this equation tells us that we have to derive the current density of the electrons, for instance, by x. Okay. And this is equal to the change of the particle density. Why? Because I have put this Q, which was here, to there. You remember, rule is N times Q. The charge density is the particle density times the elementary charge. So if you put this elementary charge here, we have this very clean equation. Plus what you do in addition, the generation rate and the recombination rate. which happens on top. So you look into this volume and you pour in something, and due to the pouring some particles additionally disappear. So this is the generation recombination portion of the change, which is your uh, contribution. Okay, so if we put in this equation here, so what is this? Here we have learned that the current density itself is a function of the electrical field, and the function of the particle density change is a function of the location. So it is the gradient, the diffusion. So the diffusion component and the electrical field component. And if we apply this mathematical equation, we end up here. What do we see here? We see if we derive an equation by x, so we have the derivative of the electrical field and the derivative, the partial derivative of the um, um, gradient. Yeah. So the change of the gradient. So the change of the gradient we have here, the change of the electrical field we have here. So this is the result applying this derivative of this equation. Okay, and for the diffusion results, we have just the second derivative because the diffusion is the first derivative, the flow rate is the first derivative, and additionally we derive it once more. And here we have the thing we have had also as before. So this continuity equation describes everything within the semiconductor as a function of the time and location. So get back and think about what we have learned. We have charges. These charges move by force, electric field, and by diffusion, concentration gradient. This movement results in a current. A current results in changing concentrations of these carriers as a function of the time. If the current in and out are different, then the level of the carrier concentration is changing. So we have everything from time to location in one continuity equation. We will not use this equation to solve it mathematically. This is the basic equation to understand the following stuff. That's all. Okay. In order to pursue our goal of carrier transport, we need additional stuff. This additional stuff is the Poisson's equation of the electrical field. Poisson, yeah, what has said Poisson? Now it gets a little bit dry. Poisson says the curl of the potential is the electrical field. Or what's that? If you have here and there the same potential, then you have no electrical field from here to there. If you have a change in the potential from here to there, then you have an electric field from here to there. That's this equation. That's it. Point one, if you have changing potentials, then you have an electrical field vector. Second, if we add an additional, um, well, it's not Laplace, but if we add a divergence to this equation, then we end up with this equation. That means, now it gets interesting. If the electrical field changes as a function of the location, then the potential changes quadratically to the power of 2. Okay, and together with the Gauss law, what does the Gauss law say? The Gauss law says you have charges in the space. If you have charges in the space, then the electrical field changes as a function of the location. Moment. What does that mean? Assume the room you're sitting in is free from charges. So where you are is free of charge. Assume that all charges are in the wall in front of you and on the wall and at the back of you. This means your room where you are is free of charges, and the electrical field does not change in this room because all happens outside of your area. Take the example of a plate capacitor. The plate capacitor, the charges are on one plate at the left side, on the second plate at the right side. So if all charges are at this location and this location, then you are looking in this area, the electrical field does not change. Where does the electrical field change? If you go over this plate, so if you penetrate this plate, you go through an area where you have charges. Then the electrical field changes from outside, 0, to inside, constant. That's the Gauss law. Let's combine them and get a very interesting linkage. Please link in your head these charges to these charges bound to the lattice and or to these movable charges caused by the dopants. Okay, if we don't have any charge, then we don't have any change in the electric field. And if we think about this equation one-dimensionally, I want to focus your concentration on these two equations. If we have charges in the room, we have a change of the electric field. If we have an electric field, we have a change of the potential as a function of the location. This is very important for me, that you take these two equations with you. Only if thinking one-dimensionally, you can understand the physics of a semiconductor if you understand these two equations. I apologize to repeat it now again, but I have the feeling that I should do it. Okay? So, um, only if you have a changing potential as a function of the location, you have an electric field. And if the electrical field changes, then you have a charge in this room you are going through. Okay? This linkage is important. Take it with you. We will understand it later on. So, for the basics of semiconductors, I have read my slides myself and flipped the slides to these questions. So, all these questions came up to my mind by reading my slides myself. Therefore, if you go through these uh, questions on page 42 and 43, you are able to answer these questions going back to the corresponding slides. Okay, so the learning objectives just help for understanding. Let's only start to understand the abrupt p-n junction. What is a p-n junction? We have a p-doped semiconductor, we have an n-doped semiconductor, we put it together, and then we have this. Okay, diet. A simple diet. But what does a diet do? A diet does do an exponential curve, v to I, and in the reverse direction, it makes nothing, and then it goes to breakdown. It's out of order. So this is the level of knowledge you should have from the third semester in my lectures, electronic, for instance. But now we will understand how to calculate the currents within the diet. So a typical diet, which is integrated into circuits, look like this. You have silicon substrate. So you have the bare wafer. On this wafer, you dope a certain area p-type. What is the doping element in the p-type silicon? Just shout it out. Don't forget to activate your mic. What is the element you use for p-type doped silicon? Boron, right. Boron has 3 valence electrons, and if you have 3 of them, you need 4, so it takes away from the lattice 1 electron. It's bound to the lattice, so it's negatively charged. Space charge is negative, and it generates a hole, and this hole is movable. Okay, so we have here movable holes. And we have here movable, no, not plus, movable electrons. So the n-type doped area is phosphorus. Yeah, so we have a p-type doped area, and within this area, we have an n-type doped area. And this happens by overdoping the p-type. You can remember? We have had these sentences when we have learned doping. If you have a certain amount of boron atoms, and then you have a p-type, because boron catches up the electrons and binds it to its valence bonds. And then you put the same amount phosphorus. So the phosphorus has the fifth electron, it gives it to the boron, and both are bound to the lattice, and it's neutral, and it's again intrinsic because the one donates, the other accepts, and the result is nothing intrinsic. So you can generate an n-doped area by overdoping with the level you need here in addition. So you have to dope in addition to phosphorus. Okay, so you can change the doping level physically. Well, then we have the so-called anode and the cathode. The anode and the cathode are both ohmic contacts. Ohmic contacts mean that the current can flow in both directions ohmically, therefore ohmic contact. Okay, and what we take now into account is this dashed box area. So all we do is examining what happens here. The rest is parasitic. You have to do it to get this diet. This is the diet area. The rest is you need it. So this box is here. So now we go into the more simplified one-dimensional visualization area. The anode is this area, this part of the triangle. The cathode is this line of the diode. What does that mean? The technical current flows in this direction. So therefore, this arrow. And in this direction, there's no current. So therefore, this line of the diode. So this is for the symbol explanation, let's say. Now let's dive into this PN type diode. Abrupt junction PN type diode. What does mean the abrupt? So previously I said it's not possible to have this, but now we assume it is possible. So at the left-hand side, we have a certain number of p-type was boron. Fernando, thank you. This boron is bound to the lattice and it is rectangular. What does mean rectangular? You remember? It is physically located at this point. It is bound to the lattice. To remember this statement, I force you to link the slide number. No idea. Here. Yeah, here. Here I have first explained what these boxes mean. They are stationarily charge carriers. Stationally means they are located energetically below the conduction band edge for the phosphorus, which is a donator, and for the boron, it is above the valence band edge. Okay, so slide number 17 gives you the sketches naming or scheme here. Okay, so what you see here, you see 1, 2, 3, 4, 5, 6, 7, 8, 9 symbolized, 9 acceptors, boron atoms. And in the same, on the same area, we have times 2 positively charged, bound to the lattice, phosphorus ions. That means your doping concentration here is 2 times higher. Or by equation, You multiply the concentration of this area times 2, you get the concentration of this area. Okay, what does that mean? That means if you bring together these two areas, something happens. On this slide, I just say qualitatively, all the movable, you see these plus signs are the holes, but here I have no plus signs. All the holes have diffused here. Why diffused? Here are many holes, and here this is an N-type semiconductor. The p charges in the N are minorities. So here are, let's say, no holes. Many holes, no holes. So they diffuse here. Vice versa. In the N-type, we have many electrons at the beginning. And if we set up this interface, they diffuse to here and neutralize the holes. So this diffusion process eliminates all these holes together with these electrons. And what you get is an area called space charge region. The space charge region is also called depletion region. Why it is depletion? Because the mobile carriers, the mobile carriers are depleted. They are recombined. Okay. This slide gives you one more important value. The space charge region O. Okay. The doping level region and the space charge region boundaries. So this is the boundary. So here is 0, minus x in the p-type, and plus x in the n-type. So if you read somewhere these variables, they define the distance from the interface to the boundary of the depletion region. And the full depletion region is called capital W. But we will learn this later. We will use it later. So here I also symbolized by concentration as a function of the x-axis the doping. So we have here the n-type doping, and here we have the p-type doping. So the p-type doping produces this concentration. The n-type doping produces this concentration of free movable particles, carriers, charge carriers. Okay, so this is the p-n junction from the point of view in the third semester. We have here movable parts, here movable parts. They diffuse, they recombine, space charge, that's it. But we are now in the sixth semester, so therefore we will have to know more. And this more, in this session, I will go through this 1, 2, with this 1, 2 slides here and here. And the next time we come together, I will repeat it and go on, because these slides are quite tough and they are very basic to the next couple of slides. So we have now, we learn now the usage of the band diagram. Okay, I haven't said very much about the band diagram on slide number 17 because we have had the conduction band edge, the valence band edge, and that's it. Now we have this stuff in addition, which will have a function of the x-axis, using all the knowledge we have learned up to now. Okay, let's start. At time 0, we are not in equilibrium. Important. We're not in equilibrium. We have the interface. Here we have the p-type, and here we have the n-type semiconductor. Let's look at the n-type semiconductor. We have here the phosphorus atoms. They have donated their electrons, and their energy level is just below the band edge. But they are in the box. They are bound to the lattice. Okay. The same game we have now here, but with the opposite sign. Here we have the boron, which has at the beginning 3 valence electrons. It has stolen 1 electron and is now fixed, bound to the lattice, 1 times negative. It has its noble gas configuration. It's okay. And now you have here a lot of movable carriers, free carriers, the holes. Again, we are not in equilibrium. You know, diffusion, I have here no holes. Is it true? No, it's not really true. You have perhaps 1 because of the mass 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 impact law. So therefore, you have a high concentration, the majority, and a low concentration in the minority. But I haven't put it here. Just forget it. For this slide. Okay, here we have a high concentration. This is the S, this is N2, this is N1, so we have a diffusion. This is also true for here. This is the intersection area, N1, N2, we have a diffusion. And the diffusion is the flow rate as a result. So we have a flow. What happens? Each electron which diffuses to here can find. Now, Mr. Muka, you said, what happens now with the injection? Where does it come from? It starts here. It doesn't end here, but it starts here. So this electron is diffusing here. Now it's here injected. This is delta N. Okay, this delta N forces additional recombination. So I would like to place, one moment, to place this slide. I will make it. One moment. Here we are. Copy. Finished. Go back to this slide. Where we are. Here we are. And I'm waiting for my iPad to react on my finger. Hasn't worked. No, it should work. Give me one more chance, okay? Where was this diffusion? This diffusion was here. So 1, 2, copy, copied, finished. Go to our slide here, then paste. Okay, so remember please, this slide we have learned to this recombination. Okay, so diffusion, recombination, diffusion, recombination. And each electron which disappears here and each hole which disappears here leaves back one not movable partner. So at the beginning, this area is neutral. But if one hole diffuses away and is destroyed, recombined with an electron, you leave back the charge in the space. And each process of this diffusion recombination makes this happen. What do you see here? The electrons have diffused here, the holes diffused there, they recombined, they left back all these charges in the space. These charges in the space, these charges in the space, these charges in the space do produce a change of the electric field. So this charge in the space does produce a quadratic change in the potential. This we will learn in the next slides. But just today, I want to just indicate that we will learn in the next slides. So these space charges quadratically changes the potential. If you multiply the potential with the charge, you get the energy, and that's the band diagram. So the band diagram is the result of the Poisson equations and the diffusion and recombination. Okay, so by having this charge in the space, you produce something else. What do you produce? You produce charges in the space because they are now effective. Poisson says there are charges, and if you have their charges, you have a bending quadratically. This bending produces electric field. This electric field forces these electrons back. So you have many of them, but they are diffusing in this direction due to the flow rate, and they are forced back due to the drift. So we have a diffusion drift. We have a diffusion in this direction. So only these electrons, which are here. So which electrons have this energy level? So energy level, high energy level. Remember the Fermi-Dirac statistics. Only very few electrons have this high energy level. Go to the spreadsheet. of mine. The Fermi-Dirac statistics are here, and the curve is here. So a very small portion has a very high energy level. The probability that there are an electron is very low. So this is the topic of this diagram. So these small numbers can diffuse. Now I just also draw this minority carrier. So this minority carrier, what happens with this minority carrier? The electric field is in this direction. If this electron, this minority carrier, gets into this area, why? It's movement, it's thermal movement. It's a probability. So if this minority carrier gets here, it drifts in this direction. And if now this drift, diffusion, no, diffusion. Okay, so it's mirrored. Here is my picture. So the drift diffusion, take the right arrow yourself. If the drift diffusion values are equal, then you are in the thermodynamic equilibrium. After you have this equality, this banding doesn't change anymore. And this is also true for the holes. The holes try to diffuse into this direction and drift back, and only very hot holes with high energy level, they can diffuse against the electric field, and these holes drift back together with the electric field. And this equilibrium will give us the chance to calculate the diode current. Okay, so to repeat these areas, this is the p-type, this is the p-type, this is the n-type, this is the diode symbol placement. We apply no voltage to these nodes, so 0 voltage, and the doping levels are equal. That means in a certain space charge area, we have a certain number of space charges, and these are equal, their numbers on both sides. So the doping level is, in these slides, in these curves, equal. Okay, so one more thing. One more thing. A diode has a built-in voltage. What we have said, Poisson equation and Gauss law said, if we have charges in the space, we have a divergence in the electric field, and the divergence in the electric field causes the quadratic change in the potential. Okay, this we know. And this results in this voltage. Okay, we have the energy, but take into account the voltage. But just divide this value by Q, then you have the voltage. That's it. So you have, due to this bending, also this voltage. This voltage is called BI. So BI means built in. It's here. You don't have to read my very good handwritten stuff. It's the built-in voltage. And the built-in voltage is now the following. We have the Fermi level here. We have the Fermi level there. But at the beginning, the Fermi level was here and there, and we have had no bending because everything was neutral. We have had no space charge. And in this situation, we have had a delta between the Fermi level in the n-type and the Fermi level in the p-type semiconductor. And this delta disappears in the thermodynamic equilibrium. Oh, fuck English. I no, lack of coffee, that's all. Um, Now, this delta, you can put it here and say the diode has a so-called built-in voltage. You cannot measure this voltage from outside because outside the potential values are defined to 0 volt without applied voltage. All is happening within the space charge region. How? We will learn the next time. For today, I think um, my capability of pronouncing English sentences with sense is over, and your capability to receive this nonsense is also over. So I think it's enough, except you have questions. No, not yet. Oh, exactly. Okay, so the zero delta you get by doing nothing, except putting these two semiconductors together. It is happening by itself. Why this Fermi level is a straight line? We will learn the next time. And you can get a difference between these Fermi levels, by applying a voltage. And if you apply a voltage, you drive the diode. And this driving of the diode we will learn later. Today we try uh, to gather all the mechanisms of doping, movable free carriers, recombination, space charge, Poisson equation, diffusion, drift. If you can put these words together and say, yes, I have learned and I have understand it, then the rest is easy. But yeah, a lot of new stuff, I know. I had a lot of time to learn that. Okay, further questions? No? Yes? Yeah, please. Okay. Oh, yes, I will do. I apologize not having done that due to the fact that I always forget it. I have also a hint. Um, One moment. Hey, by the way, my The morning lesson is on YouTube, so it's uploaded. I will put here my mobile phone number, so it's valid for all of you. If I don't see your request to come in, just call me. Just let ring my phone, and my attention is detracted to my watch and say, okay, I will have to take a look on the waiting room. Okay, don't worry. It's a lesson for you. So if you are not in, then yeah, uh, just call if you're in the waiting room and you are waiting and waiting and waiting. Let's say 2 minutes, and after 2 minutes, just call. Okay, that's all. Then have a good afternoon and a good time to the next week. Bye bye.